In planetary physics, giant planets are not supposed to go quiet like this. A world as large as Uranus should still be leaking a meaningful amount of heat from its interior, leftover energy from its formation slowly escaping across billions of years. Neptune still does. In fact, Neptune radiates about 2.6 times the energy it receives from the Sun. Uranus, by contrast, emits only slightly more than it absorbs. Recent work puts that excess at roughly 15%. That is the anomaly. Not that Uranus is cold, not that it is distant, but that a giant planet of this size has become so thermally quiet. And once that comparison is on the table, the problem stops being atmospheric, visual, or superficial. It becomes structural, because Uranus and Neptune are supposed to belong to the same planetary family. They are similar enough that, at first glance, their deeper thermal behavior should at least rhyme. But it doesn't. One world still behaves like an active thermal system. The other sits close to silence. So the real question is no longer, what is wrong with Uranus? The real question is, what kind of interior allows a giant planet to fall this quiet while a world so similar to it does not? That is where the story begins. A giant planet is supposed to release a meaningful amount of internal heat. That is one of the most basic expectations in planetary physics. These worlds form hot. They store enormous energy in their interiors, and over billions of years they slowly radiate part of that energy back into space. Neptune still does exactly that. It emits about 2.6 times the energy it receives from the Sun. Uranus does not. Uranus sits close to thermal balance, giving off only slightly more energy than it absorbs. It is not completely inert, but for a giant planet of its scale, the excess is strikingly small. That is the measurement that changes everything. Because once the problem is stated this clearly, distance is no longer enough, temperature is no longer enough, and classification is no longer enough. The question is no longer whether Uranus is cold. The question is why a giant planet of this size is releasing so little heat in the first place. And that is where the deeper instability begins. Uranus and Neptune are similar enough that their thermal behavior should not diverge this sharply without a physical reason hidden beneath the surface. If one world is still radiating strongly while the other is nearly quiet, then the difference cannot be superficial. It has to be structural. Something inside Uranus is not behaving the way our simplest giant planet picture would predict. Either heat is not being transported upward efficiently, or the interior itself is organized in a way that prevents that energy from reaching the outer layers. So Uranus does not force us to question the laws of physics. It forces us to question the ease with which we thought we had already understood giant planets. And once that shift happens, the next step becomes unavoidable. We have to stop looking at Uranus as a cold outer world and start asking what kind of interior can produce this kind of silence. If that is the fracture Uranus opens, then the next question follows naturally. Once classification stops being enough, we have to move inward. Because the only place left to look is the one place we cannot see directly, the planet's interior. And this is where the Uranus problem becomes much more unsettling. The simplest explanation would be to assume that Uranus is quiet because it has already lost most of its heat. But that explanation is too shallow. The deeper possibility is harder to picture and far more important. Uranus may not be quiet because the heat is gone. It may be quiet because the heat can no longer travel upward efficiently. That changes the entire story. In a giant planet, internal heat does not matter only because it exists. It matters because it moves. Energy rises from the deep interior toward the outer layers, and one of the main processes that allows that to happen is convection. Hot material rises, cooler material sinks. And through that motion, a planet slowly releases the energy left behind by its formation. But Uranus may not have an interior that mixes freely enough for that process to work in the way we expect. One of the strongest possibilities is that Uranus is compositionally stratified. Instead of behaving like a well-mixed interior, it may be built from layers of different composition and density stacked in a way that resists large-scale overturning. In that kind of structure, convection becomes inefficient. Heat is not erased, but its route to the surface becomes obstructed. That is the point where Uranus stops looking like a cold planet and starts looking like a blocked system. The visible atmosphere may not be the clean expression of a world that has simply gone cold. It may be the upper skin of a planet whose internal energy is still present, but trapped below layers that no longer communicate properly with the outside. And that is why Uranus matters as more than a thermal anomaly. Because once a giant planet can keep heat and still appear this quiet from the outside, the problem is no longer just temperature. The problem is transport. The problem is structure. The problem is the hidden architecture that determines whether a world can release its energy or bury it beneath its own interior. So the real shift in this story happens here. We are no longer asking whether Uranus is cold. We are asking whether Uranus has become thermally silent because its interior has learned how to trap its own heat. And once that possibility is taken seriously, one more question becomes impossible to avoid. What could have built an interior like that in the first place? At that point, the story stops being only about heat transport and becomes a story about planetary history. One of the strongest explanations is the giant impact hypothesis. Uranus is not just unusual in temperature, it is also unusual in orientation, rotating with an extreme axial tilt that already suggests a violent event early in its past. And if a collision was powerful enough to tip the planet so dramatically, it may also have been powerful enough to reorganize its interior. That is what makes the impact idea so important. It is not just a visual explanation for why Uranus appears to be lying on its side. It is a structural explanation for why Uranus may no longer behave like a normal giant planet from the inside out. A collision on that scale could have melted, displaced, and redistributed material throughout the planet. Under extreme pressure, that rearrangement may have produced stable density layers, compositional boundaries, or a deep insulating region that weakened convection and slowed the escape of heat. If that happened, then the thermal silence of Uranus is not an isolated feature. It is part of a much larger system. Its tilt, its weak internal heat flux, and its unusual interior may all belong to the same physical history. And that changes how Uranus should be read. It is no longer just a cold giant. It is a world whose present behavior may still be carrying the consequences of an ancient disruption. In that sense, Uranus is not merely quiet, it is structurally altered. And that is what gives the planet its real significance. Not that it is mysterious for its own sake, but that its current state may only make sense if we treat temperature, structure, and history as parts of the same story. So by the time we arrive here, the question is no longer just where Uranus's heat went. The deeper question is whether Uranus became thermally quiet because its interior was rewritten very early in the life of the planet itself. By the end of this story, Uranus no longer looks like a simple cold planet at the edge of the solar system. It looks like a world whose silence has to be explained from the inside out. What begins as a strange thermal measurement turns into a much deeper physical problem. Uranus is not quiet because physics has failed. It is quiet because the physics of heat transport inside a giant planet may be far more complicated than our simplified models once assumed. That is the real lesson Uranus leaves behind. Not that it is an impossible world. Not that giant planets are beyond explanation. But that surface similarity is not enough. Uranus and Neptune may belong to the same planetary family, yet Uranus shows us that category alone cannot explain outcome. To understand a giant planet, we have to ask how heat moves, how matter is layered, and how an ancient event can continue shaping a world billions of years later. And that is what makes Uranus so important. Its silence is not empty. It is diagnostic. It tells us that the deep architecture of a planet can matter more than the label we place on it. So in the end, Uranus is not just a cold giant. It is a giant planet whose present state may only make sense if heat, structure, and history are read as parts of the same system. And that may be the clearest thing Uranus teaches us. A world does not need to break the laws of physics to surprise us. It only needs to follow them in ways we were not yet ready to understand.